today we will be covering lecture 5, and essentially let us review what we had done last time. So, we were talking about the various material selection criteria for biomems, biochip kind of devices. We talked about issues like optical transparency, biocompatibility, then rapid photo definability or rapid fabrication strategies that could be done using these materials. So, these are some of the important selection criteria. We also tried to describe some of the basic silicon processes borrowed from the microelectronic industries, which can be used for MEMS applications. We talked at length about some of the commercially available silicon devices like the digital micromirror device, accelerometers, the single chip microphones, and also the AFM technology, the atomic force microscope technology. We started with some of the alternative fabrication strategies using polymeric devices and covered some portions on soft lithography like replica molding and contact printing. So, we are going to go ahead on this spree and try to finish the soft lithographic processes today, after which we will do a little bit of introductory electrochemistry. So, the next process along the line is capillary molding. It is again one of the important processes for especially for display technologies sometimes. So, the process steps are very simple. You have again a mold made up of PDMS with these small micro capillaries made by replication and molding techniques, okay. And essentially then we spin coat a thermosetting resin paste on to the surface of a substrate. In this case substrate may be a silicon or a glass wafer, and then we essentially press this PDMS mold on the top of this thermosetting resin and press it up till the resin actually takes the shape of these small micro capillaries, okay. And once it is fully, so the essentially the PDMS when it sits on the top of this thermosetting resin, it squeezes the material in both directions, and so there is of course the material coming out from these ends, and the material also kind of getting filled into these capillaries, as you can see, okay. And then you peel off the PDMS and create the surface of a PDMS by just some pre-processing in a manner that it leaves intact the resin material filled in these micro capillaries, and this is what micro capillary molding is. It is a very good patterning technique which can be used to coat polymeric pixels on the top of a substrate, okay. Now, some of the practical issues that come while doing this is that number one is that there is always a tendency because of surface tensions for this angle theta to be developed between the wall of the microcapillary on the PDMS and essentially the resin material, okay. And so, these several processes are basically coating the paste, capillary infiltration, and releasing the mold, so that you are left with the thermosetting resin shaped as small dots, okay. So, these are some of the features and structures which are generated by this process, cited from various illustrations. So, the overall process steps are that you create a master and replicate a polymer layer to create micro capillaries, spin coat the resist to be patterned, contact the polymer replica for resin to go in the capillary with some limitations and restrictions like these kind of abnormalities, and they usually have a thermosetting component, and so the replica can be released to obtain the ribs which are thermally set, okay. The next process is dip and lithography, and in fact this is again a process wherein we can write selectively molecules on a surface. This process was generated by Shadmerkin's group at Northwestern, and essentially if you look at this process, there is a substrate which is again coated with some kind of a film which can selectively adhere to molecules, maybe thiolated DNA, and here this right here is an AFM tip, and what we do is that we create some favorable temperature and humidity conditions, so that there is this layer, this monolayer of water, and we choose the surfaces in a manner that there is a tendency for this water meniscus to adhere more to the AFM tip than the substrate, and so you can drag it along with the tip as the tip moves around. Okay. So, the idea is that the idea is that this particular layer, as you are seeing here, of water is more adherent to this AFM tip surface than the substrate on which it is moving, and so when you are dragging the pen, this moves along with the pen rather than adhering to the substrate. Okay. So, why it is used? This is used for transporting molecules. So, if you have some kind of a constant feed mechanism or delivery mechanism wherein these small molecules can be delivered rapidly onto this AFM tip, they can use this monolayer to go and set in a particular arranged order onto the substrate of interest. Okay. And so, therefore, this process is used for essentially writing molecules, and so it is pretty much like what an ink pen does. In an ink pen also, especially in a fountain pen, there is ink within the tube and it goes through the tip of the pen, and due to capillary action of the paper on which it is writing, the ink is essentially adsorbed onto the paper. Now, this is also a similar kind of an application with an STM pen doing the same job, and instead of ink, this pen writes molecules rather on the surface. So, this is a highly commercial process used rapidly, and in fact, there is a company by the name of Nano Ink Incorporated, where they have commercialized this dip pen lithography technique for a lot of applications, wherein self assembled monolayers and DNA, proteins, etc., are rapidly delivered onto such surfaces. And typically this process is a serial process, but there are some initiatives in which they have tried to make this process parallel, wherein there are several such AFM tips which are actually being fed by the molecules all together, and then when this whole probe head moves with the different tips, it can be able to write in different tracks and routes these molecules. So, there is an initiative where this serialized process is being currently commercialized for an array of cantilevers for parallel writing. So, another challenge here in this kind of a mechanism is how the molecules can be rapidly delivered and continuously delivered onto the STM pen, and principles of microfluidics are off and on used for that purpose. So, if you look at this particular illustration from Merkin's group, as you can see here that as the tip speed inverse increases, that means as the tip speed decreases, the line thickness of these molecules automatically increase, which actually also intuitively makes sense. And so this is a very important process again, which is kind of grouped into the soft lithography domain. Another very important process is compression molding, and this also forms a foundation of something called nano imprint lithography, that we'll be just talking in the next slide. So, in this process again there is a material which is the substrate, and a thermoplastic material is coated onto the substrate, and the mold again is prepared and made which can withstand high heat and pressure. Okay. So, this mold can be in silicon nitride or silicon dioxide over maybe a silicon surface, or even made with metal, micro machined with some other techniques like EDM, electro discharge machining, ECM, so on and so forth. So, once this mold is pressed onto this thermoplastic material, there is a shaping of this thermoplastic material as the negative for the mold that is used for the squeezing. Okay. And then the idea is that you remove the mold, and so whatever remains here is well set, and thus the features on the mold are transferred, the negatives of the features on the mold are transferred onto this material. This is how you write micro features or structures onto a surface. So, the very common compact disc that we use regularly in our computers or audio equipment is essentially realized using the compression molding process. And another very important technique which is often on used is injection molding, which is illustrated here in this particular figure. So, if you see this this illustration here, there are two dies which are kind of mating components, and there is a small gap here in this region between the dies, which is the shape or the feature which has to be replicated. So, a polymeric material which is normally in the solid form is dropped into this hooper, and this lead screw essentially transfers the material by first melting it and then constantly feeding it onto this small cavity, and as the polymer melt goes into the cavity, it stays there and gets cooled off and gets hardened or solidified, after which the injection or this mold is kind of separated or opened and the material is removed. So, you really need a very good surface pre-processing agent here for a proper separation of the polymer that you feed in. So, in fact, this is a very useful process for again microfabrication. So, in a nutshell, these processes are about taking a patterned hard substrate which is capable of withstanding heat and pressure without with minimal deformation, and essentially a thermoplastic material spun over some kind of a wafer is molded by compressing the mold onto this particular thermoplastic film, and then the ensemble is heated so that sets up the thermoplastic material and the mold is removed eventually. So, another very important process which comes almost immediately from compression molding is nano imprint lithography, and I would like to just illustrate that this process has also been made or being included in the ITRS roadmap, especially for end of the road devices. Here as you see here, the same process as compression molding is used, but on a much smaller scale, on a submicron scale. These are some illustrations of what nano imprint lithography can do. In fact, this is actually a set of pillars which are about 10 nanometers in size, and there is an array of such pillars which are made using a nano imprint mold. Okay. You could do a variety of other processes, like this particular illustration is that of a PMMA, which is also an e-beam resist, wherein these 10 nanometer diameter holes have been made and an array of these holes have been realized onto the polymethyl methacrylate, and these are through holes. Okay. So, this can be used as a shadow mask for processes like deposition, where this mold is put over a wafer and material like gold or platinum is deposited through this shadow mask, so that these small tiny tiny dots here are each of about 10 nanometers in diameter, because they can go through this particular hole on the PMMA. So, the shadow mask is later on removed and you have an array of these fine dots, and these are used off and on for a lot of micro nanoscale electronics. So, in a nutshell, again nano imprint lithography is the extension of the hot embossing process, and all you need is a nanoscale master for this, and especially this process has been added on very recently to the ITRS roadmap. So, this kind of brings us to the end of the type of polymeric methods available for microfabrication processes. We will now turn back to our initial line of thought on sensors, which we had done, which we had covered even last lecture and before, and we would look into a little bit of fundamentals of electrochemistry or electrochemical sensing. And essentially if you look at again the different transduction types, I would just like to reiterate this from the last few lectures, that the electrochemical transduction can be characterized into potentiometry, which is the measurement of cell potential at zero current, and if I may just add, it is a method in which the voltage is proportional to the log of concentration of the analyte of interest. Voltammetry, where you use the oxidizing and reducing potential of a material to sense the material. Conductometry, where you are rapidly monitoring the conductance change. Conductance is again the reciprocal of resistance of the electrochemical cell, and by using the conductance you can find out whether there is any change in the concentration of the analyte, or you can use this using AC current bridge method, wherein impedance measured at a certain frequency can be seen and the change can be monitored for gauging the concentration, the rapidly increasing or decreasing concentration of a certain analyte. So, let us look into a little bit of fundamental aspects of what happens really when we dip a metal rod inside a solution. Okay. So, when a piece of metal such as, let us say, zinc in this case, is inserted in water or maybe a solution which contains zinc ions, there is a immediate charge separation in the boundary. And this I think I illustrated in one of my lectures before, that whatever processes take place at this interface lead to the rapid development of metals from the electrode going into the solution as metal plus ions. So, some oxidized states are created, okay. And simultaneously the electron which is liberated, in this case, in case of zinc it is 2 electrons, are rapidly concentrated around this particular area of the electrode. So, it is a self stopping process, because by the principle of electroneutrality, this combination cannot hold beyond a certain level of negative charge. It would automatically try to stop this process of zinc going into solution and creating electrons. Okay. But once the zinc goes into the solution, there is also another effect which is happening, that the water from the surroundings kind of comes between the zinc and this negative charge on the electrode and forms a thin dielectric layer. So, essentially we are talking about a very small capacitance which results from the positive charges in terms of the zinc ions which is in the solution and the negative electrons separated by a small monolayer of water. Now, this layer can be as thin as about 10 nanometers, okay. But this self stopping process essentially develops something called a dual layer of charge, and all electrochemistry is essentially about the number of charges that cross through this interface dual layer between the two phases, solid and the liquid. Okay. So, once this concept is clear, let us look it into a little more detail of what may happen to the electrical double layer. So, essentially the interfacial potential in such a double layer may be of the order of a few volts, okay, which essentially makes the electric field very high, because if you consider the span or the spatial separation of the positive and negative charges, it is not more than about tens of nanometers. Okay. So, therefore, 1 volt across about 10 to the power minus 8 meters would make about 100 million volts per meter. That is how high the electric field is really going to be in such a double layer. What happens, let us say, if another illustration here, if a piece of zinc is dipped in copper solution. Okay. So, let us first actually consider why it is or how can this oxidation of the metal, which we were seeing in the last case where zinc was being converted into Zn plus 2, can be increased for a little longer. Okay. So, as we know, this is again driven by diffusion, this process where the zinc is going into water as a plus 2, and because of the principle of electroneutrality, there is only a finite amount of oxidation that can happen. Okay. So, how can I extend the oxidation time is the question. Okay. And this is very, very important for developing a basic understanding of what electrochemical sensing is all about. That is why it is important to go through these some of these concepts. So, a simple way to keep the oxidation process going is to immerse the piece of zinc from water into rather a solution of copper sulphate. Okay. So, copper again is an electrically active material, and also there is a tendency of zinc to displace copper from its solution. So, this generates something called a redox couple, okay, wherein the first process that takes place is, okay. So, let me first say what is going to happen if such a zinc is dissolved inside the copper sulphate solution. So, it immediately becomes coated with a brownish coating of finely divided metallic copper onto the surface. And if you look at why this is happening, essentially the copper which was present in the copper plus 2 state in the CuSO4 solution, okay, gets reduced by taking electrons which have been generated in this metal as the zinc tries to move out as Zn plus 2. right. And so therefore, the 2 electrons which are already present in this particular lump of zinc by virtue of the oxidation of zinc. And by the by, why, how do we know what is oxidizing? Just a little bit of basics here, that the valency of a material should increase for an oxidation process to happen, right. So, oxidation is signified by, here the valency is 0, here as you see it is +2 because 2 electrons have gone out. So, oxidation is essentially the increase in the valency of the material. So, copper goes from a copper +2 state into simple copper, maybe in the solid form. This is the brown deposit that we are talking about, right. And the zinc on the other hand gets converted into Zn+2 and leaves 2 electrons back in this surface, which is easily donated away to the copper ion to get converted into copper solid. So, if I look at this equation together, it becomes something like that the zinc has a potential of displacing copper +2 from its solution to make into solid copper deposited on the surface, and the zinc in turn gets oxidized. So, this is also known as a redox reaction, right, because one element here, the copper, is getting reduced. Mind you that the valency is changing from +2 to 0, okay, in the solid state, and one component, the zinc, is getting oxidized where the valency is changing from 0 to +2. So, these two are going together. So, it is also known as a reduction oxidation or redox mechanism. Well, the next obvious question that anybody would ask is that how can we keep the continuity of the oxidation process going on. Okay. So, once we have this process a little bit extended, the next goal is how can we keep this process to go on. Okay. So, one way of doing it would be that, let us say we have something which is able to be displaced into the solution as ions, and something wherein it is able to displace the ionic state into the solid form, right. So, zinc here as you see getting oxidized to Zn+2 and going into the solution, and copper from this copper nitrate getting reduced and going as a deposit onto the copper electrode. So, if I connect both these electrodes together, then the electron which is liberated here can flow all the way through to this particular electrode, and it can easily reduce the copper here, right. But this process will only happen finitely, because after a while there would be an increase in the Zn+2 concentration, right, inside this particular solution, because of which there would be no further transportation of zinc into this solution as Zn+2. So, in effect what would happen is that the ionic concentration of Zn+2 would increase here, and it would stop this electron flow process, because there is no more oxidation taking place, and it would be a self stopping process. So, can I do something to make this process continue? The answer is yes. So, what we do here is that we create a charge balance back by connecting the two solutions together as well by something called a salt bridge, right. So, essentially this is something wherein it contains two plugs at both the ends, and there is a ion exchange solvent, and there is a continuous exchange of the increased, let us say, SO4 -2 ion on one side in the copper sulphate solution, with the increased Zn+2 ion on another side with the zinc sulphate solution. And so, therefore, this creates the charge balance between the two cells or two half cells, and this process goes on for some time. Okay. So, this is also known as an electrochemical cell, right, electrochemical cell, and in fact this is also called as a Daniell cell. So, what I would like to illustrate here is that there is a sign convention which is used for writing such half cells. Okay. So, the convention which is followed here is essentially the anode is where the oxidation would occur, right, and the anode is represented in the convention more onto the left side, right. So, anode is where oxidation takes place. So, zinc is converted into Zn+2 is really called the anode, okay, because we consider the solution perspective of it as if it is giving positive ions into the solution, and cathode is where reduction is happening. This right side of this particular convention is the cathode, and of course there is an electron flow from the left electrode to the right, from the electrode which provides oxidation to the electrode which provides reduction, and the current essentially is the opposite of the flow of electrons, because it is conventional to consider current flow as positive. So, the current would flow from the cathode to the anode, okay. It is in the opposite direction. So, this is what happens when the cell operates in a spontaneous direction, okay. So, following the sign conventions, there can be other kind of electrodes which can work out in pretty much similar way, and these electrodes would be essentially off and on used for electrochemistry later on, where we will talk about how to sense analytes using some of these basic principles, electrochemical principles. So, the other form of electrode which exists is an ion-ion electrode, where when you talk about, as you have seen in the last illustration, we talked about really two solutions, one oxidizing, another reducing, and two different solutions, one in copper, one in zinc, with a copper and a zinc electrode respectively, each of the solutions. Here we are talking about two different oxidation states of the same material. So, in one state iron here is available as Fe+2, and in another state it is available as Fe+3. So, assuming that if this Fe+3 is the oxidized form of the material and Fe+2 is the also oxidized form of the material, but essentially with a difference of one electron between them, there is still an electron flow from the anode side to the cathode side, and this is essentially again a working set of electrodes and a flow cell essentially, and a battery. So, essentially so we are talking about that sometimes electrochemical reactions involve only ionic species, such as in this case the +2+3 form, and if neither of the electroactive species is metal, instead of, so we need something to provide the connectivity, right. So, in this case we use an inert metal which is platinum, let us say, and this acts as a conduit for providing or for picking up the electron from the anode side and placing it onto the cathode side. The other types of electrodes that are available are gas electrodes, as can be illustrated here in this particular example. So, here instead of a liquid species, we are concerned with a gaseous reaction, okay. So, it is a gaseous species, such as let us say hydrogen, oxygen, chlorine, etc. And if you look at this particular reaction, what is again happening is a reduction, is an oxidation process, okay, wherein the chlorine which had a minus charge here is getting converted into a zero valent state or a gas form, and at the and the cost of one electron is eliminated from the chlorine. So, it is an oxidation process essentially. So, some materials here like platinum are again used as a conduit for electrical activity or for promoting connections between two or more cells, but the material itself is inert and it does not participate in the electrochemical reaction or the electrochemical process. Another form of electrode here is the insoluble salt electrode. Here the concept is a little different, like let us say if we are talking about an AgCl electrode, okay, a silver chloride electrode. So, normally silver chloride is an insoluble salt in water. So, if you put AgCl, it precipitates as crystals. So, the problem is in that case what do you do with the electrochemical sensing or electrochemical cell design. So, in that case essentially what you do is you take a silver wire and cover this with a thin coating of silver chloride, and that formulates a good scheme of ion exchange, even though the salt considered is highly insoluble in water. So, these are some of the types of electrodes that are used off and on for electrochemical sensing, apart from the conventional metal electrolyte electrodes. Another very interesting factor is that some metals are more active than others. in the sense that they provide or they can displace a less active one from a solution of its salt. Like let us say if we consider the zinc copper case, or if we consider this Daniell cell, as we saw here that the zinc was displacing, or was getting displaced or getting oxidized and going into the solution, and was really displacing the copper +2 state as a deposit, a copper deposit onto the electrode. So, zinc was able to clearly displace copper from its salt solution. So, I can consider zinc to be more electroactive than copper ions. Okay. So, based on these kind of ability of materials to displace each other from their solution state, there is a scale of electroactivity, especially of metals, which have been formulated on the ability of the metal to displace hydrogen from water, steam or acid. Okay. So, it is essentially that if you take H2O in any form, be it steam or be it kind of in equilibrium with an acid, or be it just in the water state, how the metal can displace hydrogen, or how actively it can displace hydrogen, also gives it a position up the ladder on the electroactivity series. Why hydrogen? Because a common scale is needed for it is like a reference scale. Okay. So, if it is compared with respect to the hydrogen, it gets compared with each other by that process. So, if it is way up on the electroactivity series, it can easily displace something which is below it on the same series. Okay. That is how these series are being made, and some fundamental basics of electrochemistry are important for understanding how really measurements can be made in electrochemical sensing. Okay. So, let us again look at the same example of Daniell cell. So, you have a metal electrode, you have a solution, salt solution, you have the M1 is the type of metal here, and you have another metal M2 in its salt solution S2. Okay. And you have connected them or interconnected them using this salt bridge, and you are trying to take a readout of the total current across between the two electrodes. And obviously, if M1 is the anode, then the electron flow would be from M1 to M2. Okay. So, let us say M1 in this case is zinc +2, and M2 in this case is copper +2 and copper. Okay. So, M2 and S2 are essentially copper and copper +2, and M1 and S1 are essentially zinc and zinc +2. So, if you consider the total EMF that this particular cell would have, it is essentially the EMF of the right side of the cell, or the right cell, minus the EMF on the left cell. This is more so because, as you know, current's conventional direction is from the cathode to the anode, right. In other words, the current really is going in this particular direction. So, if the current is going in this direction, we can safely assume that the potential here V right is higher than the potential in the left side, and the delta V which is responsible for movement of these electrons is essentially V right minus V left, as you can see here. Okay. And if we consider what really the E right or the V right is, it is nothing but the voltage provided by the copper minus voltage of the sulphate solution S2, and similarly V left is voltage provided by the zinc minus voltage of the zinc sulphate solution. Okay. And therefore, the total overall EMF of this particular cell can essentially be represented as the right V copper of the electrode minus left V zinc of the electrode. So, the solutions really do not play much of a role, and more so because there is a salt bridge which keeps on interconnecting and neutral or making the solution electron neutral at all points of time. So, one thing is very obvious here, that the half cell potentials can only be measured relatively, and absolute values cannot be determined irrespective of how hard you try. And how really can you do it, because the very factor is that the double layer, the electric double layer which is responsible for this potential to build up, is a very small layer. So, you cannot tuck in a small piece of metal in this 100 nanometers or 10 nanometer domain and get a relative potential of the electrode with respect to the solution surrounding the electrode. So, the only other way is a relative measurement. However, this problem can be averted by making a reference electrode and defining that as an electrochemically inactive electrode. Okay. So, with a 0 electrochemical potential, although in principle such an electrode would have some potential, but if we consider a scale wherein this potential is signified or represented as 0 potential, then this can be a reference electrode for considering the individual potentials of different metal electrodes with respect to it. So, this reference electrode in this application has been universally accepted to be the standard hydrogen electrode, which is essentially something like this, where there is a platinum and there is a 1 molar solution of HCl in water, and hydrogen is bubbled through this particular electrode at about a pressure of about 101,325 pascals or 1 atmosphere, and essentially there is a potential which is created. Yeah. So, basically the standard hydrogen electrode now therefore is something which is realized by a metallic platinum immersed in an aqueous solution containing hydronium ions H3O plus, which is formulated by again a 1 molar HCl in water, and hydrogen gas is slowly bubbled over this. So, at 1 atmosphere pressure. Okay. And temperature is fixed to be again 25 degrees Celsius in order to get standard conditions. It is called the standard temperature pressure STP conditions, and consequently the potential for this electrode is taken as a reference 0, although the actual potential in this configuration comes out to be about 4.4 plus minus 0.02 volts at 25 degrees Celsius. Okay. So, let us actually move on to the aspect of how we can calculate, how we can predict what is the current level, what is the potential difference between a pair or a combination of such electrode solutions, and how we can predict the flow of current, right. So, again as you know that for let us say any any metal solution combination, the total E cell is represented by E right minus E left, right, and the right is essentially, as in this case, this particular case, the cathode, and the left is the anode, right. And so, if we consider an electrode where we are talking on one side of the standard hydrogen electrode, right, and the other side to be the particular metal of interest. So, how can we really write this redox couple is the question. So, here for instance in this particular cell, when we are writing a combination of a metal solution and a metal with respect to the standard hydrogen electrode with platinum as the conduit, hydrogen is getting oxidized at the cost of releasing 2 electrons, and these 2 electrons are gathered together by the metal, which converts from the +2 state into the solid metal. Okay. So, this redox reaction can be also written as H2 plus M2 plus makes 2H plus MS, as can be illustrated in this particular equation here. For this particular cell again, E cell is represented as the voltage on the right side minus the voltage on the left side. So, essentially it is the voltage of metal minus voltage of solution plus voltage of solution minus voltage of platinum. So, we define this voltage of solution minus platinum to be 0 because that is the scale of the SHE or the standard hydrogen electrode, and so therefore, the E cell comes out to be nothing but Vm minus V solution, and we call this the absolute potential of the particular metal ion combination. Okay. So, very useful again to find out. We can actually get a couple of these E0 cells for a different combination of different metals and its salt solution, and these have been kind of illustrated here in this table. Like for example, if there is a conversion of the sodium ion into solid sodium, there is an E0 with respect to the standard hydrogen electrode of minus 2.71. The minus here indicates that rather the sodium gets oxidized like zinc, as we have illustrated before when you connect it to a hydrogen electrode. Okay. Similarly, zinc has a negative potential, and this goes all the way up to lead, and so lead up to lead, all these different metals are more electroactive than hydrogen, and so they displace hydrogen from its plus state or oxidized state and reduces into a gaseous state when connected to a standard hydrogen electrode. The potentials are reverse and positive when you connect the standard hydrogen electrode to below these like mercury chloride, silver chloride, copper, cuprous kind of solutions, so on and so forth. So, it is very easy now to find out the standard potential of the cell and also to predict the electron flow direction if this scale here with respect to the SHE has already been formulated. Like in the case of the Daniell cell, if we look at there is an electrode here which is the anode converting into Zn plus 2, and an electrode which is the cathode converting from copper plus or cuprous state into copper 0 state. So, for the standard cell potential in this case would really be actually nothing but E right minus E left, which is E copper minus E copper sulphate minus E zinc minus E zinc sulphate, and these are nothing but also E0 copper and E0 zinc. And if you look at this particular electroactive series here, the E0 copper comes out to be about 0.34, and the ink excuse me, and so it comes out to be about 0.34, and the E0 zinc here, as you are seeing, comes out to be minus 0.76, right. So, this is copper, this is the zinc. So, the total E cell can be represented as E right, which is 0.34, E0 right, I am sorry, with respect to the standard hydrogen electrode, minus E left, which is minus 0.76, or in other words it would be 1.10 volt. So, this is essentially the total EMF of the cell. So, you consider the individual electrodes with respect to the SHE or standard hydrogen electrode, and then make a combination of these two to easily find out what is the potential of the particular cell. Some other numerical examples. This is a very interesting example again, wherein you are considering an iron-iron electrode. Okay. So, there is a ferric and a ferrous state here, plus 3 and plus 2, and you are coupling it to copper and cuprous state. Here this actually is the cathode where there is a reduction process going on, and this is the anode where there is an oxidation going on. So, what would be the cell reaction in this case? So, the cell reaction would be that the Fe3 converts into the Fe plus 2 state by giving 1 electron. Mind you, again, as I had earlier illustrated, platinum here is a inert non-participative metal, which is just a conduit which takes out the electron or the charge from this particular solution, right. And on the cupric side, on the cuprous side, the Cu2 plus gets reduced into Cu, giving 2 electrons. So, in order to balance these two, we can easily write the final solution as Cu plus 2 plus Fe plus 3 twice should be able to give you twice Fe plus 2 plus Cu. This is just for the purpose of charge balance. So, you have to generate 2 electrons here for these 2 electrons to compensate for the 2 electrons which is needed to reduce the copper to its copper plus copper 0 state. Okay. So, this is how the final cell reaction of this particular galvanic cell would look like. There are a few more illustrations here. This is a very interesting problem. For the case of the silver chloride electrode, we can couple it and form a redox couple with a cuprous copper combination, and in this case the standard potential of the cell can be calculated by considering the reactions. So, the right side again, that is the cathode, is a conversion of the Q plus Cu plus 2 form to Cu 0 at the behest of 2 electrons which is liberated in the process. And in the silver chloride side, if you look at, you have this twice Ag or twice silver plus 2 times chlorine minus giving twice AgCl. So, effectively you are oxidizing the chlorine, okay, or you are trying to make the chlorine electron less and generate 2 electrons here. So, these two coupled together would formulate a redox reaction wherein twice silver plus twice Cl minus plus Cu2 plus, right, especially these 3 would react to give 2 AgCl and Cu. So, this is essentially the cell reaction that would happen. So, if I want to generate what is the standard potential of this particular cell. So, as this process involves so essentially there is a reduction in the chlorine state, or there is oxidation in the chlorine state, right. And so, therefore, it would be the E right, which is E copper in this particular case, minus E E0 left, which is E AgCl in this particular case. Okay. And essentially if you look at the table before, where we are talking about the the standard reduction potentials, this particular illustration here represents the reduction of AgCl really, right. And so, the reduction of AgCl is given with respect to a standard hydrogen electrode to be plus 0.111 volts, right. And so, therefore, if you look at the potential here, you have 2 times this particular reaction, right, and in the opposite sense. That means, here the Cl minus is oxidized to a Cl plus 0 state. So, the E cell potential of this should be exactly minus 0.11 volts. This process is happening in the reverse manner as would have normally happened if you coupled this to a standard hydrogen electrode. So, the E cell potential here is essentially 0.337, that is the potential E0 of the copper, or the right side of this particular representation here or notation here, minus twice 0.111 volts. So, it comes out to be 0.115 volts. So, since this potential is positive, the reaction will proceed to the right. Okay. So, the next illustration is again very interesting problem, wherein we talk about the work done by an electrochemical cell, and we are slowly trying to gauge the voltage equation, which is also known as Nernst equation. Okay. And here we first try to derive this equation, so that we can have a direct relationship between the voltage and the log of concentration. In fact, this is a preliminary level study for the potentiometry as an area of sensing or diagnostics. So, let us first talk about what is the electrical energy that is spent when a bunch of electrons or a bunch of charges is moved from one side of the cell to the other side. So, there is an EMF of the particular cell, let us say E dash cell here is the EMF of that particular cell, against which there is a kind of total amount of charge transfer of C trans magnitude. Okay. So, against the potential E cell there are about C coulombs of charge that are being moved. So, the total amount of electrical energy in this case would be represented as E dash cell times of C trans, right. So, essentially charge into potential is the total work done or the electrical energy spent. So, C trans or the total amount of charge can also be represented as the number of moles of electrons which is being transferred in the process into the total charge per mole of the electron, which is also known as the Faraday constant F 96,485 coulomb. This gets generated by multiplying 1 mole size, which is 6.23023 10 to the power of 23 times of the electronic charge, which is 1.6 10 to the power of minus 19 coulomb, right. So, this is essentially 1 mole of electrons total amount of charge. So, if we want to write this electrical energy as with these particular notations, the number of moles of charge transferred and the Faraday constant, we can easily write this electrical energy to be NF E dash cell, right. Okay. So, we can think about that the maximum work that is done by the system, and because it is a work done, we are considering a negative sign here, and is also equal to the free energy of the system delta G. This is the Gibbs free energy, which is the maximum work that a system can do or has a potential of doing. So, the delta G can be easily equated to the free energy can be easily equated to minus N F E dash cell. Okay. This is the amount of work which has been already done in order to transfer NF charges through a potential E dash cell in a particular illustration. So, the delta G can be equated to minus NF E dash cell. And there is another very common illustration coming from the Van 't Hoff equation, where delta G is equated to the equilibrium constant of any reaction K, okay, as minus RT ln K, and we will be actually coming to this a little bit later, probably in the next slide. So, therefore, let us first talk about how this Van 't Hoff equation comes into picture from thermodynamics. So, the Van 't Hoff observed for the first time that if you really plot the natural log of the rate of any reaction with respect to the inverse of temperature, and this actually he found for a system of gases. Okay. So, there is a strange kind of linear relationship between the two. This can be illustrated more in this particular curve as you are looking at. So, this is essentially the axis which represents the natural log of K, okay, where K is the equilibrium constant, and you are plotting this with respect to the inverse of temperature. And so, for different gas systems, he found out systems of gases and these are equilibrium processes essentially. He found out that there is a linear relationship between the inverse of temperature and the log of K. Okay. So, what is really the equilibrium constant? This comes from another illustration called the Le Chatelier's principle. The rate constant of any equilibrium process is of really any forward reaction is proportional to the product of the activity of the products totally created or the activity of the products totally which are created by a reaction raised to the power their stoichiometric coefficients. Okay. So, if in this particular case alpha moles of A is reacting to beta moles of B to generate, let us say, sigma moles of S and tau moles of T. So, by the Le Chatelier's principle, the equilibrium constant for the forward reaction is generated as S, the activity of S to the power sigma into activity of T to the power tau by activity of A to the power alpha into activity of B to the power of beta. So, we would like to actually continue this and some other illustrations probably in the next lecture. Thank you.